Now, today's one of those days where often if we spend this extra day in a section and we have some connections to make, basically we're going to take some ideas that we've already learned and apply them to even something that's new. But there's not going to be some like big bomb drop here. You've learned about capital F of F or capital F of B minus capital F of A, and we're going to just kind of keep using that to look at some extension kind of problems. I want you to see this one in the book because, well, when you finally do your assignment, you'll end up doing some of the other problems that surround it. So just kind of look at it. I see some of you are already sketching it, which is probably a good idea. You might want to sketch. But do you see the directions, how they are asking you to find what's known as the book calls it the total shaded region. I want to kind of add to that concept the word absolute. I want you to also think of it as the total absolute area. I want to add that word absolute to kind of the directions. So what does that mean? How are we going to use what we've already learned to try to find this total absolute area? Okay, now there's some things that I would assume that you can apply to this. Maybe there'll be something that catches your attention that you might not realize. First of all, if you look at the shaded region, well, it's pretty obvious that there's like two of them. We sort of have this region that's up here, and then we obviously have this region down here. Notice, though, that both those regions are between the graph and the x-axis. That's good, because that's the way integrals work. It's always the region between the graph and the x-axis. Okay. Notice that one of the regions, we shouldn't be surprised, will come out to be positive. Well, this region right here will technically come out to be negative. And here lies one of our first kind of make sure you realize that if we're trying to find the absolute area, then we're going to eventually take this negative area that we're not going to be surprised, right? We're not going to be surprised that comes out negative, but we're going to take it and we're going to make it absolute. We're going to basically make it positive. Okay, so that's what's implied by these directions. Now, there's something you've heard me say before. It was on a video, but it definitely doesn't hurt to hear it repeated because it becomes kind of a pretty important idea as we get to the end of this chapter. And that's the place where these positive and negative areas seem to change. The place where the positive area switches to be the negative area. Okay, now I'm not trying to trick you here. It's the x-intercept. But I'm just saying that is super important that you notice, that you identify, that you use the x-intercept. And the way that you'll use the x-intercept, and you've heard me say this before, is that you will subdivide. You always subdivide with the x-intercept because the positive and negative area has its changeover at that place. Okay, so I kind of put this up here, but again, if somebody asks you to find absolute area, you're going to have to see it. It seems kind of obvious because we've been looking at it for the last 3 minutes, but if I ask you to find the absolute area, and I will somewhere down the road, there's always a sketch involved because you have to be able to see. You have to be able to see the subdividing. Okay, and I will kind of draw your attention to that as we keep going. Now, I think it was the first thing I said, but we can kind of come back to it. the area in this problem is between the graph and the x-axis. And if you're saying, well, of course, Mr. Naylor, isn't that the way it's supposed to be? Look at some of the other ones that surround this problem. Not all of those areas are just between the graph and the x-axis. If you look right above number 19, it's kind of a different type of area. But this problem, it works out between the graph and the x-axis, which means that all we really need is the antiderivative. All we really need is capital F of x, because that's what capital F of x does. It gives us that type of area. So let's find it. Let's find it. It'll be important. It'll obviously be part of our answer. I want you to be okay if your antiderivative doesn't work out to all be integers. If you take 3 and divide it by the new exponent of 2, well, you're going to get 3/2. That's fine. If you take x and divide it by the new exponent of 3, so again, it's fine. It doesn't have to like cancel out nicely, but our antiderivative, we just added to the exponents and divided by the new exponent. Okay, now, maybe it's not going to be a big surprise to you that to find this total absolute area, we basically just need to find 2 areas. One of those areas is from 0 to 3. The other area is from 3 to 4. This is what we mean by subdividing. Really, we're just finding 2 for the price of 1. We're just finding 2 areas. Remember, we're not going to be surprised that the one area comes out negative. Remember, we subdivided with the number 3, but we have to split this into 2 separate areas. And now we go to town. Now we go to the business of finding them. Just some things to note here. When you finally do this like on your own, some of the numbers repeat. So we don't need to calculate over and over, but I do need f of 0. I will need f of 3. I will need f of 4. I'm kind of saying that we can kind of get these numbers prepared. We can find them and then go use them as needed. Okay, the order that I wrote these numbers down might seem backwards from yesterday. That's because I'm just kind of finding these numbers so we can then take them and subtract them for each of those integrals. So you can kind of calculate them, get those answers. Yes, I'm going to give them to you, but make sure you understand that you're plugging into the capital F of x. Obviously, when you plug in 0 and square it and cube it, you're still going to get 0, so that's nice. When you plug in 3, you're going to square it, you're going to cube it. You're also going to make sure you multiply it by those fractions. Sometimes this is the place where the mistake is made, so just be careful when you plug in 3. Maybe you're trying it right now, or just, you might trust me, it comes out to be 4.5. Make sure you trust yourself. And then when you plug in 4, you get, I have the decimal version of this, but you get to 266. That's fine. We can write down the decimal. You could change it to a fraction too. Okay. I don't like where I wrote that because I need that space. So I'm going to just recopy it here. Now, we've got 2 little integrals to find. So we're going to find the integral from 0 to 3. Well, that's f of 3 minus f of 0. So that's, well, that's the numbers that I found already here. That's 4.5 minus 0. Okay, now just make the connection with me. It's not supposed to be too tricky, but that 4.5 was the area of this region from 0 to 3. There's no tricks going on here. Okay, we have that piece. We have that part of our answer. And then over here, I'm going to find the answer from 3 to 4. Now, be careful. It's f of 4 minus f of 3. So we can go over here and grab those numbers. We already found them. And here's where I'm saying that we shouldn't be surprised that will come out negative. That will come out negative. And, we're kind of glad that it did. Okay, that means that we're calculating this value correctly. Again, I have the decimal version of this, so I'm going to write it that way. It's negative 183, repeating as much as we want. Negative 1833 is this area. Now, because the problem said from sort of the beginning to find the absolute area, I added the word absolute. That's what the book meant. That means that we are going to add our two areas in an absolute way. So, yes, this one's already positive, but we have the right. We will want to make these absolute. So it's going to be a positive 4.5 and a positive 183. Okay, and that comes out to be 6 1/3. Or if we change that to a fraction, or if we use fractions the whole time, it's 19/3. Okay, that's our total area of that shaded region. Now, this starts to get a little more fun when you are given the task of finding an area that involves the x-axis, but maybe involves more. Okay? After lunch, you guys are going to be tasked with trying to solve number 18. I know that you're kind of thinking about it right now, so I'm just pointing out that number 18 is going to involve some of what we did here, but it's also going to involve some additional thinking, and you're going to want to experience that. So I'm not going to say any more. It's a neat problem, and we'll let you guys kind of run with it after lunch. What I would like to do is show you guys one more sort of application of integrals. It will seem kind of random, but you'll find out that it connects. It actually has to do with something known as an average y value. An average y value. You can write this down if you want, or you can just kind of think about it with me. Don't worry. You didn't miss anything. We didn't talk about this yesterday. But right now what I want to do is see if we can consider what would be the average y value of the function y equals x from 0 to 4. If you guys keep taking math classes, I hope that you become a student that's willing to try to explore something new without just waiting for the teacher. You may find yourself in a lot of those spots if you go on to college and you're given things to kind of figure out, but it could be in any class, obviously. Here's what I'm doing. I'm trying to do some stuff that I know, that you know, that's the graph of y equals x. Okay, all of us can draw a diagonal line. So there's the graph of y equals x. Continuing, we could think about what's given here. That is a certain interval that goes from 0 to 4. So, we can kind of focus on that part of the graph now. Now, be careful. You might be tempted to find the area or maybe think about the area, but nothing up here is really kind of given that away. There's nothing up here that says find the area, but it will involve the area. I just want to think about y values with you. I want to think about y values. Now, Would you agree that there's some y values along this graph? I mean, certainly, any y value. Let me guide you a little bit. Why don't we think about some y values that match up with some common integers? Now, indeed, there's other y values besides just the ones that match up with integers, but are you thinking about some y values? Not too hard to think about, are they? They are, including the first one, they're just equal to the x values. If somebody throws some numbers at you, 0, 1, 2, 3, 4, and they say to find the average of those numbers, well, what would you do? If somebody threw some numbers at you and said to find the average, don't worry, it's not something that you haven't done before. Yeah, let's check it out. So we're going to add up the y values. And we're going to divide by, that is correct. Okay, even though the number 0 doesn't seem to affect the average, it does actually, because it counts as a number from 0 to 4. Okay, hey, this is right. Okay, this is the right answer. You should be getting 10 over 5. You should be getting 2. Okay, the average y value from x equals 0 to x equals 4, or if you will, from y equals 0 to y equals 4, is going to be the number 2, which, you know, kind of makes sense for this problem even. Of course, it's like right in the middle. Okay, now, by the way, if we had put some decimals in here, if we had put decimals and we had kind of equally thought about the decimals that would be in here, we would still end up with the number 2. Okay, technically, we should be thinking about every y value from 0 to 4. But of course, we can't really do that, okay, because we don't have the ability to add an infinite amount of numbers with this type of concept. But 2 is the right answer. Now, you know this has to have something to do with integrals, right? You guys have been around learning long enough. We've spent time talking about integrals and area. So this problem has to also connect. So let's think about it. Let's think about the integral connection. Are you willing to write an integral? We don't do enough of this where we ask students to kind of create. What integral would you create that you think would connect to this problem? It'd be the integral of x, okay, probably from 0 to 4. Okay, now remember, if you're asked to do the integral of x from 0 to 4, okay, you have different ways that you can do that. You could go back to sort of the time before. You could go back to the time before we had antiderivatives, and you could just find the area of this. I want to make sure that you realize that the area of that triangle has always been and will always be the integral of x from 0 to 4. So if you're feeling a little bit like some geometry, if you're feeling a little bit like a base and a height, then you're finding the area. If you're kind of like, hey, what about this capital F of x thing? Sure. Okay, it's pretty cool. It's called the antiderivative. It especially is helpful for problems that are not just nice little triangles. And as we talked a lot yesterday, you have to plug in b and a, but individually, the number that you get for b, individually, now that comes out to be 8, and individually, the number you get for 0 They don't mean anything. They don't mean anything until I subtract them. So 8 minus 0. Now, of course, that still equals 8, which, by the way, was also the area of this triangle with a little bit of that kind of thinking. Oh, darn it. The integral is 8. I was kind of hoping that that would come out to be the same. Well, we really actually weren't hoping. If that was true, then something wouldn't make sense here. So what's the connection? Maybe to say it another way, how can we use the integral? How can we use the area to get the average? How can we use 8 to actually get 2? There's kind of one thing we have maybe not taken into account. Okay, and I would argue it would be the word average. You know, we kind of just like found the full area. So how can we take that area and sort of average it? You would just need to divide it by your interval, okay? Because your interval it started from 0 to 4. That's how this all started. And it's kind of like taking your area and dividing it or averaging it by that interval, okay? In other words, I can divide it by 4. And now I end up with the same value, which is the average y value. What just happened here? Well, what happened is we used an integral. We used an integral, which is, as it's always been, the integral of f of x from a to b. And we divided it by, or as you can see right here, we multiplied it by 1 over the distance of our interval, the span of our interval. And when you do that, you get what's known as the average y value. Now you have to do these two things. So again, you have to divide it by the length of the interval. And of course, the thing that you'll divide is this area that you get from A to B. Okay, so the average y value will always be the integral divided by the length of the interval. The integral divided by the length of the interval. Now, there's something you'll realize as you do a few of these problems, and that is that you will always attain the average at some point between A and B. There'll always be some point, C, that gives you, that is equal to that average. For the problem we did here in the beginning, that was x equals 2. Because at x equals 2, I attained the average. So the average y value will always be somewhere in the interval. All right, let's try one that's not just a easy little triangle. Let's find the average y value for the sine function from 0 to pi. Let's find the average for the sine function from 0 to pi. don't know if you're big on it, but I think you know that I am. I want you to understand what we're doing. And it's kind of interesting, actually. There's that old sine wave. Okay. It's got a lot of y values on it. Now, when's the last time you thought about the y values of a sine function? Probably not recently, but think about it with me. The sine function is only able to reach a y value of 1. So like all the y values are between 0 and 1. And look, there's like y values on this side and there's y values on this side. I wonder what the average is. I wonder if it's just a half. Okay, well, let's find out. And of course, to find out, all you have to do is take 1 over the length of the interval. Now, the length of the interval is just going to be pi minus 0, which is pi, but we'll show it, times the integral of sine. Now, there are times in math where something that you learned, you can like use in the next problem. What I'm talking about is that we have learned and seen the integral of sine now a couple times. Because the integral of sine is just the area. Yeah, 2. Okay, you don't have to memorize random stuff in here, but sometimes you recognize that you already know that the answer to this is 2. Okay, so pi over 2 times, or 1 over pi, 1 over pi times 2. Two over pi. Now, you could pop that in a calculator if you want to, but 2 over pi is almost like 2 over 3. Almost, right? 2 over 3. Oh, that's like 2/3. It's actually a little bit above a half. So even though a half might be the number in the middle, it turns out that the average y value occurs a little bit above a half, which is actually pi, or 2 over pi. Okay, now when you guys come back from lunch, what we'll do is we'll find C, because that's also always part of this process. Finding C would be like finding the place where this occurs, which is just going to be those 2 points on that graph. But we'll do that when you come back. I don't want to squeeze it in. You always find the average by dividing the integral by the length of the interval. So we find the integral. Okay, I could have used capital F of x. I just didn't because we've done that a few times now. And then you divide it by the length of the interval. So 2 over pi. Now, 2 over pi is a y value. It's important that you realize that now what we're in search of is an x value. But the book calls it finding C. Okay, now, you don't need to make a sketch. A lot of this chapter is visual. If you're ever stuck or kind of wondering what's going on, well, make a sketch. So I made a sketch. Here's 2 over pi. It's intersecting at 2 points. So we actually have a C1 and a C2 that we want to find. Okay, this is kind of a little unique because it's a sine function. Here's the part that's not unique. And this is like the part where I hope you're like, yeah, that makes good algebra sense. This is y. This is y. All I have to do is plug it in and solve for x. Okay, notice I'm just going back to the original equation. So 2 over pi, plug it in, and solve for x. Now you guys will do this with some other kinds of equations. Some of them might just be like a parabola or something kind of normal, or maybe it will be a trig function. If it's a trig function, remember that you have to do the inverse. You have to do the inverse of 2 over pi. Now look, it wouldn't hurt for you to play along and do that on your calculator, okay, because the kind of answer that pops out here isn't guaranteed to be some kind of pretty number. But you're going to do the inverse of 2 over pi. Make sure your calculator's in radian mode. And that's going to solve for x. At this point, decimals are fine. Okay, decimals are fine. You get like 0.69. 2 decimal places is probably fine too. Okay, so that's C sub 1. That's like our first C value. If you were back in trig class, we would say that that would have been the principal value. It's sort of like the first one. But what about the other one? Okay, now I'm sure you realize that if you put it in your calculator and hit enter again, you're still going to get 0.69. But we have to do a little thinking. It's not completely a trigonometry thing, but it's helpful to know what's going on visually, that red distance right there, that red distance is 0.69. And so is this red distance. So all we got to do is realize from where. It's 0.69 from pi, right, from pi. Okay, so my C sub 2 can be written as pi minus 0.69. I give you credit for that. Okay, and maybe you put that in your calculator and you take pi minus 69 as a decimal and you get 245. Okay, so this problem has 2 answers. Again, it's kind of unique. Make sure you realize what's going on. We're simply saying that at 0.69 or at 245, that the sine wave attains its average, that the sine wave will equal 2 over pi. And that's always going to happen somewhere. There's a neat application for average y value for like something worthwhile, but right now it's just for the sake of finding it. All right, now the problem that I'm giving you, this is like an important step in your little journey. It's a problem that is purposely going to cause you to connect some of what I did at the beginning of the period with some of what we have done in the past, and maybe even something new on top of that. Why don't you put it on this little half sheet of paper? I know some of you are already getting writing, but go ahead and use my paper. One more thought. Some of the textbooks, well, all of the textbooks have been used by other students, some of them more heavily. And some people have drawn things on top of this problem. I really caution you against using what they drew, because who knows? Who knows if what they drew was a good idea? You might even want to erase if there seems to be like a pencil line. I would prefer that you draw your lines on the scratch paper. Make sure you at least realize that this problem is more than just the integral from 0 to 2. I'll say it's really a lot more than just the integral from 0 to 2.